All right, let's do this. A super fast revision of electric charges and fields. We're going to cover the absolute must-know concepts for your board exams in just the next few minutes. So, let's jump right in.
You know that little bit of static magic? Yeah, it's not magic at all. The real answer lies in the fundamental concept we're talking about today, electric charge.
So what is charge? Well, you can think of it just like mass. It's a fundamental property of matter. But here's the difference. Where mass is the star of the show for gravity, charge runs everything when it comes to electricity and magnetism.
Now here's a classic mistake people make. They think a neutral body has no charge. Nuh-uh, that's not true. It just has a perfect balance of positive and negative charges. And here's the key rule, the thing you have to remember. You can only charge something by moving the tiny electrons around. You either add more to make it negative, or you strip them away to make it positive. That's it.
Okay, so how does this stuff actually behave? Is it just random? No way. Charge follows three simple yet incredibly powerful rules that govern absolutely everything.
First up, we've got additivity. It's super simple. Charges just add up with regular math. Then there's conservation. This one's huge. You can't create or destroy charge. You can only move it around. And finally, quantization. This means charge comes in these tiny identical packets. You can't have half a packet, ever.
Okay, if there's one rule you really need to lock in for your exams, it's this one: quantization. The total charge, which we call Q, on any object is always a whole number n multiplied by the charge of a single electron, E. You can have one electron, you can have a million electrons, but you can never, ever have half an electron.
Right, so we know what charge is, but what happens when two charges actually meet? Well, they exert a force on each other, and this is where things get really interesting.
And you already know this one, you've known it for years. It's the fundamental rule of interaction. Opposites attract and like charges repel. It's that simple, but it governs everything.
And of course, there's math behind it. This is Coulomb's law, and it puts a number on that force. The force F is directly proportional to how big the charges are, but, and this is the key part, it's inversely proportional to the square of the distance between them. What does that mean? Well, if you double the distance, the force doesn't get cut in half. It drops all the way down to 1/4. That's a huge deal.
But, this is where electricity gets really different from something like gravity. See, gravity doesn't care if you're in the air or deep underwater. The electric force, though, it changes dramatically depending on what's between the charges.
See, every material has something called a dielectric constant. You can think of it as the material's ability to get in the way, to shield the charges from each other. Its own little particles literally interfere, weakening the force between them.
And for water, that number isn't small, it's a whopping 80. Let that sink in. This means the force between two charges in water is 80 times weaker than it would be in the air. This isn't just a fun fact, it's the brilliant reason why something like salt, which is held together by electric forces, dissolves so easily in water. The water just comes in and completely shatters those bonds.
So, how do they do it? How do charges exert this force from a distance? They don't just magically know the other one is there. No, they communicate through an invisible field of influence.
The best way to picture it is like a web extending out from the charge in all directions. Anything that happens to wander into this web is going to feel a force. That whole region of influence is the electric field. So, how do we measure how strong this field is? We call it electric field intensity, and it's actually super simple. It's just the amount of force experienced for every unit of charge you place at that point. So, the unit is just newtons per coulomb. Makes sense, right? Now, to actually see these fields, physicists came up with a simple universal rule. By definition, field lines always radiate outward from a positive charge, and they always point inward towards a negative charge. This isn't just a random drawing. This simple rule lets us instantly predict the direction of the force anywhere in that field.
All right, enough theory. Let's put this stuff into practice with a classic board exam problem.
You're going to see this one a lot. Examiners love asking for the null point because it's the perfect test. It checks if you understand field direction, Coulomb's law, and your basic algebra, all in one neat little package. It really tests the fundamentals.
Okay, so here's the setup. You've got two positive charges, but notice, one is 4 times stronger than the other. The question is simple. Where on that line between them is the net electric field going to be exactly 0?
The logic here is actually pretty straightforward. First, you know the point has to be between them, right? That's the only place where their fields are pointing in opposite directions and can cancel out. Second, you just set the strengths, the magnitudes, of their fields equal to each other. And third, you just plug in the formulas we talked about and solve for the distance. And remember, for your boards, showing these clear, logical steps is just as important as getting the final number right.
Okay, so if you're in a hurry, this is your slide. These are the absolute core concepts. If you understand these 5 points, you've got a really solid foundation for this entire chapter. So I want you to remember something. The rules you're learning for this exam, they aren't just abstract theory in a textbook. They are the fundamental principles that scale up from the tiniest atom all the way to the particle accelerators and the smartphone touchscreens that literally define our world. So when you master these concepts, you're not just passing an exam, you're understanding the invisible forces that shape everything around us. Good luck.